Infinite limits. So most rational functions have vertical asymptotes at values which cause the denominator to equal 0. And think about that. Think of any function that'll cause the denominator to equal 0, therefore creating a vertical asymptote. So, for example, f of x equals 1 over x minus 1. So we know that when x equals 1, the denominator is 0, so x cannot equal 1, therefore we have a vertical asymptote at x equals 1. So let's consider the graph for 1 over x minus 1. And I do want you to draw this graph in your notes. And if you notice that the limit of 1 over x minus 1 as x approaches 1 from the positive side continues to increase. So as it approaches from the positive side, it continues to increase and it goes to positive infinity at that vertical asymptote. So the limit of 1 over x minus 1 as x approaches 1 from the positive is positive infinity. And consider now the limit of 1 over x minus 1 as x approaches 1 from the negative side. Well, if we approach the vertical asymptote at x equals 1, my function seems to decrease, and it keeps going all the way to negative infinity. So the limit of 1 over x minus 1 as x approaches 1 from the negative is equal to negative infinity. So pretty much, if f of x approaches positive infinity or f of x approaches negative infinity, as x approaches some value c from the right or from the left, then x equals c is a vertical asymptote. Don't just think that if the denominator is equal to 0, then we automatically have a vertical asymptote. It's great to bring back your prior knowledge, and x values that cause the denominator to equal 0 will produce a vertical asymptote. It's nice to think of it that way because there are cases when that'll work, but not all the time. There are exceptions. So an exception is when there is a common factor between the numerator and the denominator. In other words, when you can simplify the rational function. Now, try to think of a rational function where you can simplify so that the denominator also simplifies. Try to think of a rational function where the denominator with the numerator will simplify. For example, f of x equals x minus 2 over x squared minus 4. This function will produce the denominator of 0 or the denominator will equal 0 when x equals 2 or x equals negative 2. However, we do not have a vertical asymptote at x equals 2. If we were to consider the limit of this function as x approaches 2, we would see that it exists. So, well, first things first, we got to do, we want to check direct substitution first, and obviously we get indeterminate form, so we move on, and we simplify. You can factor the denominator to x minus 2 times x plus 2, and then simplify x minus 2. So now we're taking the limit of 1 over x plus 2 as x approaches 2, and we can go ahead and do direct substitution here to get our answer of 1/4. So the limit of f of x minus 2 over x squared minus 4, as x approaches 2 is 1/4. So the limit exists, however, f of 2 was undefined. Therefore, we have a removable discontinuity at x equals 2. So just because x equals 2 made the denominator equal to 0, that didn't tell us necessarily that we have a vertical asymptote. In this case, we don't have a vertical asymptote at x equals 2. We have a hole at x equals 2. So let's go ahead and look at the graph for this function. So you can see that we have a hole at x equals 2, but we still have that vertical asymptote at x equals negative 2. By the way, for the record, you do need to draw this graph. But why do we still have that vertical asymptote at x equals negative 2? Well, when we simplified x minus 2 over x squared minus 4, we were left with 1 over x plus 2. And notice that no matter how much we simplified the original function, we still have an issue with x equals negative 2. X still can't be negative 2. So we have a vertical asymptote there. And I'll show you how to determine whether a function approaches positive infinity or negative infinity as it gets closer to that vertical asymptote. I'll show you that in another video. As for now, this concludes the video.